There we go. All's right with the world. Okay, so we have an exam on Friday. That's the big thing, right? If you're looking for help and you're available this afternoon, so I'll just say it's always Monday, Wednesday, although it's not. Monday is gone, but I'm available for appointments. And so if you want to talk to me this afternoon, just let me know after class. And then on Thursday evening, there'll be a help session at 7:30 p.m. on Google Meet. And the link, as always, is in the syllabus for that. So today is a review day. We have covered all the information that we were going to cover before the test, so there's no new stuff to present, which is always nice. What do you guys want to ask about? Particular problems you'd like to see worked? The stuff that I did at the end of class. So I'm going to have to remind myself. So hybridized orbitals. Yeah, I was wondering if it was hybridized orbitals. So the hybridized orbitals, that's actually for your lab. So when you get back that week, you're going to have a lab and they're going to talk about orbital hybridization. And orbital hybridization is really important and used a lot in organic chemistry. So that's part of why they're doing it, so that you'll have a lab, you'll experience it some, and then when you see it in organic chemistry, it won't be so new. But I'm not going to put it on the test. Okay. So it is important, but it's not as important for Gen Chem as it is for organic. Yes?
Can you go over naming compounds?
Yeah, let's go over naming compound. That's great. That's great. So, so let's say we have two types of naming that we're going to do. So when we name compounds, we have ionic compounds, and we named ionic compounds a certain way, and then we have covalent compounds. All right, so the first thing, how do you know if a compound is ionic or covalent? Anybody have a thought here? Yeah. Tyler. Right. Right. So covalent compound involves sharing of electrons, and an ionic compound, what you've got is the attraction between two opposite charges, really. Okay. You can talk about electrons being taken. You could imagine the electrons being taken from one of those elements to another one, or you could just imagine the ions exist already, which is usually how it is. The actual reaction of an electron being taken from one compound and given to another is usually like super. There's this concept of exothermic that you've seen probably the wording for in your book that I'm not going to worry about you knowing right now. We'll cover more of it later, either this semester or next. But gives off a ton of heat, like explosive, when that happens. But ionic. So let's go ahead. Ionic is the attraction. So ionic bonds, which go into ionic compounds, are the attraction between opposite charges. All right, in the I actually asked about this one in the practice test. In my answer I said full charges. Okay, right now all you know is full charges, right? Things are +1, +2, -1, -2, -3, things like that. Okay, later on you'll learn that there are partial charges. Okay, and that's why when I say that almost 90% of chemistry is charges, it's because we can have little bitty charges and we can have really big charges, and they're all important, and it's all about explaining what's going on with that. But so ionic bonds are the attraction between opposite charges, and covalent bonds, I'm going to just say form when electrons are shared between atoms. All right, but that's not how we know. That's great. That's important stuff for us to know. That's important for you to know. But not exactly obvious how you know when that happens and when that doesn't. All right, so if I looked at the periodic table, how would I know whether I had a covalent bond or an ionic bond? Anybody remember? So covalent bonds or covalent compounds. Covalent compounds form between nonmetals. All right, and so this is where those regions of the periodic table become important to us. Where are nonmetals on here? See the staircase? Nonmetals are all these. Okay? So nonmetals are from the staircase over this direction. All right? And metals are everything over here. So covalent compounds form between nonmetals, and ionic compounds form between a metal and a nonmetal. Or a metal and a polyatomic ion. Remember those? Okay, those are like they're covalent compounds that have a charge. All right, so let's go ahead and start out with covalent compounds. That name is perhaps easier. I find it easier. So naming covalent compounds. All right. Remember, you have prefixes, and you'll have to memorize these prefixes. Hopefully you have them memorized already. All right, so your prefixes are going to be, put this down here. Your prefixes are going to be mono, di, tri, tetra, etc. Penta, hexa, I'll do all of them. Septa, octa, nona, deca. Okay, so that's your prefixes 1 through 10. You're going to say the name of the element. So say the name, and we're only going to name compounds with 2 elements here. Okay, all our naming so far has just been with 2 things. Say the name of the first element, then the next, well, let's say that again. Say the prefix or write the prefix. Let's do write because you're not going to be saying it. Write the prefix in front of the name of each element. All right, we have an exception. Don't say mono if it's the first element, if it's one of the first element. Chemistry is full of exceptions. Exception, don't say mono, or don't write mono if one of the first element. All right. First element, you just name the name of the element. Name it. Second element, chop off the end and add "-ide". All right, so those are our rules. So if I have this compound, all right, that would be carbon tetrafluoride. Okay? I didn't put wasn't monocarbon tetrafluoride because there's one in the front. If I had, let's say I had this, just how it's written, okay? This would be dinitro tetrahydride. Just the way it's written. Okay? What if you had this compound? How would you name that? Go ahead and try that. What'd you guys get for that one? Carbon disulfide. Okay? Those are pretty straightforward. For ionic compounds, so for ionic compounds, we don't say the number of things. You're going to infer the number of things or figure out the number of things based on the charges. So ionic compounds have to neutralize. Don't use the prefixes. The charge is neutralized, and so you can figure it out based on what's in the compound. All right. You're going to use when you have a single element, so you name the first, you name the first one, name first atom, the metal. All right, so calcium, potassium, etc., aluminum. Name the first metal. For the second element, if it's an element, what you're going to do is chop off the end and add IDE. Okay? If the second thing, the second ion, is a polyatomic ion, then you're going to use the polyatomic name. And there are 9 of those that you need to memorize, okay, that I gave you. Your book has more. I narrowed that to 9. Go back and look at the notes. So if the second ion, because they're both ions, the metal's an ion, the non-metal is an ion. For the second ion, if it is a polyatomic ion, just use the name. Okay, and those things, and you have sulfate, you have nitrate, you have nitrite, sulfite, carbonate, bicarbonate, ammonium. The first, let's add an exception here. We have we have one polyatomic ion that's positively charged, and that's ammonium. So I'm just going to do exception ammonium. There are more polyatomic ions than that, but ammonium is the only one that is common enough for general chemistry. And I'll start off with ammonium, just so we know how we use that one. All right, so if my compound was this, NH4 is ammonium, okay, and it's an NH4 plus, and I'm going to put it with oxide. All right, I'm going to erase that plus because I'm going to give this and we're naming, and then we'll go back and do the reverse. So ammonium oxide is what this is. Actually, I've got to put parentheses around that and do that. All right, because my charges need to neutralize. That's why I had to write this way. Ammonium has a +1 charge, right? I know that because I memorized it. Oxygen has a -2 charge. How do I know that? I look at the periodic table, right? And if I add 1 electron, 2 electrons, I now have for oxide, or 8. If I go 1, 2, I get to 10. That's the electronic configuration of a noble gas, and that's super stable. So I know that oxygen is -2 because I can look at the periodic table and see that's what ion it makes. Yes?
So, I'm just gonna word this, but I know that for some, like, compounds, there's like a regular number in front of, like, a set of atoms or elements or whatever. Would we not be able to do that for the ammonium, so it'd be like 2 NH4?
Good question. Good question. So we haven't balanced equations yet. So the question is, why doesn't the 2 go here? Yes? If the 2 goes here, a 2 here means it's times everything. So that would mean I have 2 ammoniums and 2 oxygens. So if I had to take that 2 away. The subscript 2 here means I have 2 of what's in the parentheses here, or for here for the 4. If we just look at the 4, it means I have 4 hydrogens, I have whatever of what's right next to it, or if I have parentheses, I have however many, in this case 2 of everything in the parentheses. Great question. Okay, any other questions before we go on? Yes?
So like, how do we like determine the difference, or how do we determine using the suffix of like "ide" and "ite" and "ate"?
Right, okay, good question. How do we know when it's "ide" or "ate" or "ite"? "Ide" is always when you have a single element. Okay, so let's go and see some of those. So, you know, it could be anything in those first 3 rows of the periodic table. All right. I'm not going to give you anything because some of the things down lower don't act like that. But because of that staircase, right? The staircase cuts into it, it becomes a metal. But if we look at this, if we go F, B, R, Cl, whoops, they're not in order, iodine, okay? But this is fluoride, bromide, chloride, iodide, okay? So these all get ide. Okay. Same thing with oxygen, 2-, sulfur, 2-. Could do selenium. And then we'd have nitrogen, 3-, and phosphorus, 3-. All these would also get IDE. Okay, does that make sense? Those all get that. But then we have these polyatomic ions that you're supposed to have memorized, right? And then they all have special names. So this is ammonium. I'm going to just do all of them quickly. This is sulfate. This is sulfite. This is nitrate. This is nitrite. Let's see, I've done, what, 5? So I have 4 more I've got to remember that I gave you. We have hydroxide, which is very important. we will see it later. We have, so that's what, 6? We have carbonate. I think I gave you carbonate. We have bicarbonate. We have phosphate. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm hoping that matches the 9 I gave you earlier. If it doesn't, there's one off, and I'll hopefully look at it and not get it right. I saw somebody nod, so I'm hoping it matches. I picked off the 9 I thought were most important in terms of what I've seen most often in my career. Okay? Okay, so that's how, so in terms of the different name at the end, or the not an I, it's one of these, okay? Hydroxide, it actually got 9 at the end anyway, but it is an O and an H. It's essentially a water without an H plus. All right, so let's go ahead and try some more of these. How would I then name, what if I had calcium and a phosphate, all right? And I need to get my numbers right here. That. How would I name that? Yeah, calcium phosphate. So naming these is going to be pretty easy when you see them, okay, for the most part. Right? It's going to be going the opposite direction that's going to be more challenging. So what we've got this compound here. I'm going to make you believe that they're all 3 and 2. What's that? Somebody over on the right-hand side? Mg is magnesium. By the way, I'm going to find some periodic table. I think for your last exam, I gave you a periodic table with names on it, maybe. I'm going to give you a periodic table names on it. I'm not going to tell you what the names are or where the names are on the periodic table. So I haven't asked you to memorize where anything is, but it would behoove you to do enough practice problems if you have a decent idea where it is, right? And, we have this whole periodic table here. I might direct your attention if I gave you something like lead, which I might give you, right? Or anything below this row right here. Okay, but really the ones you need to be familiar and be able to find fast are kind of this and up. All right, so you don't have to, don't try to memorize and get good at all these. But you can get good at these in terms of finding them quickly. All right. Like I said, you'll have a periodic table. It will have names on it. People had plenty of time for the last test, so it may not be a problem, but you don't want to be spending ages trying to find an element on the periodic table, right? Did somebody, while I was chatting or while I was talking, come up with what the name of this was? Magnesium nitride, yes. Okay. And actually, they'd be lowercase. I write everything in uppercase, which is maybe confusing, but none of these get capitalized. They are not that important. They're generic. They're not proper names. Okay. I'm not going to, and I'm also not going to grade you on capitalization. Yes.
So putting those compounds in parentheses, like you did for the phosphate there.
Yes.
Is that just because it wouldn't be fair to assume that if there is a compound in parentheses, it's going to be one of those compounds that you listed above?
Yeah, so that's a good point. So if something is in parentheses like this, it's going to be a polyatomic ion. Okay. You wouldn't put you don't put the nitrogen in parentheses because there's only one of them. Okay. All right, so let's try this, let's do one more example and then let's try this the other way. So, if something is if a metal is in one of these first two columns, we know the charge. These are all +1, these are all +2, right? And it's because they lose 2 or 1 electrons to have an electronic configuration of a noble gas. But if something is out here, it becomes more challenging. Okay, you don't know exactly what those are. And so it needs to be specified. And often they have more than one possible charge or one stable charge. And so that would then be specified when you describe the metal. And so in terms of naming, I might have something like this. I can have, let's say I have iron, and I have, and then here you would have to determine the charge based on what you had. So let's say I had iron like this, FeS. All right, I'm going to have to, because I'm in the middle there, right? I'm in the middle of the periodic table, I'm in the transition elements. I need to determine what the charge is on that iron, because it could be, iron it could be +2 or +3. You don't need to memorize that, all right? But those are the two charges you get. Actually, you kind of do need to memorize it because we have that cuprous, ferrous, right? Okay. But for copper and iron there. But if you don't memorize that, that will probably not be big points on the test if it shows up at all. All right. Not a core concept, but possible. You could be possibly asked. Anyway, what did I do? Iron. So I don't know whether it's +2 or +3, but I do know what sulfur is. What's sulfur? What's the charge on sulfur?
-2.
-2, right. So if sulfur has a -2 charge, and so I'm just going to make some notes. This is me notes. This is work doing the problem here. Okay. When you write out ionic compounds, don't be writing charges up here in your final answer. You could actually write them for work and then cross them out. But I need to know that you're not writing them and thinking those charges, that's the way you write it. So if these charges are going to neutralize each other, this has to be 0 charge overall. What's the charge on iron have to be? +2, right. +2 plus -2 is 0, right? So it's going to need to be, here, let me do charges like they're on your car battery. 2 plus, right? If I add these two together, I get 0. And so what you say is you say the charge in the name. You say iron. You put a Roman numeral 2 because it's the +2 form. Sol what? Fide. Right. That makes sense? Okay. Yes.
That just apply to metals.
What was that?
When you put
The charge? The question is, does it just apply to metals? And it does just apply to metals, but it's even more specific. It only applies to these metals. The ones between my hands here. These are the transition metals. It only applies to those metals. Okay? It also applies to these metals, but I'm not going to ask these. All right? So it applies to the lanthanides and the actinides, and we're just not going to worry about those that much. If you go on in chemistry, you can worry about them more. Questions? Yes.
So do you figure out the charge of the transition metals based off of the other element?
Yes, exactly. So the comment was, the observation was that you are finding the charge of the metals based on what the other element is, the one you know. You will have something you know, okay? Either a polyatomic ion or an element that you can figure out what, or non-metal, that you can figure out what the charge is based on the periodic table. Let's go the other way for the ionic compounds. That can be more difficult. The covalent compound's pretty straightforward, right? If it's a covalent compound, it's made of nonmetals, pretty straightforward to go from the name to the the compound. Somebody wants me to do an example later, I'm happy to do it. But, so let's say I give you something and I say, lithium, let's go ahead with, I'm trying to mix these up. Lithium bromide. Write the formula for lithium bromide. And here you're going to use the charges. Okay. Anybody have it?
Li plus Br minus.
Okay, LIBR. We're not going to put the charges in. So LIBR, right? Too easy. Okay. This one is a plus. We could write it as a 1 plus. This one is a 1 minus. And you can imagine bringing this charge down here and this charge over, or this charge over here for numbers, and then we don't write ones. All right, let's try one that's a little harder. Let's try potassium, which is K. Potassium sulfide. Okay, anybody have it? So it's going to be K, and then we'll have an S, but then we need to get some numbers in here. K2S, right. And so the way we know that is potassium is +1 based on where it is in the periodic table. It's number 19. And sulfide is going to be 2 minus, where it's on the periodic table. And then you can imagine I'm going to put this 2 down here, and I'm going to put this 1 over here. And so K2S. Does that make sense? Okay. Let's do a polyatomic ion. Let's do calcium phosphate. And remember from above, phosphate is this. All right, what do you guys think?
Ca3 parentheses PO4 2.
Ca3, PO4, parentheses, 2. Okay, very good. So what that is calcium has a +2 charge, phosphate has a -3 charge. I'm going to go ahead and bring these down and bring this over, and that's how I get it. And then you want to remember your parentheses. Yes?
So basically, like, at least in this problem, like, phosphate is like a packaged deal, like, that's always gonna be together.
Yes.
So that's why the parentheses are here.
Yes. So the comment was that, the observation was that phosphate or any of our polyatomic ions are always a packaged deal. They're actually covalent compounds that have a charge. And so they all come together, they stay together, and you have those 9, can't do 9 in one hand, but 9 that you have to memorize. Yes?
So can I assume that if we see those 9 on the test doing this, we should know that we're gonna be succeeding that, right?
You should know. What was that?
They're gonna be getting parentheses and it's gonna like.
Yes, yes. Whenever you see them, there's going to be parentheses unless When would you not use a parentheses?
You don't have to put any numbers on it.
If there was only one,
Right.
right? Okay. All right, let me do one more here. And it's going to be complicated from two perspectives. Let's do lead for let's do sulfate. I'm going to make it super complicated. I will remember, I'll remind you right now, but I won't do this on the test, that sulfate looks like that. And lead is PB. It's down here, it's number 82. I gave you that one on the test, I would tell you where it was, because it's below this fourth row. All right, does anybody have that one? Okay, good. So almost all the way there. I've got one more rule I want to teach you. So you went with PB2, SO4, parentheses 4. And what you were doing was you had 4 plus and 2 minus, right? And then we took this and put it here, and then we took this and we put it here. Remember, for our ionic compounds that we always do these smallest whole number ratios, right? So this would get you half credit for this one. So Jack, did you want to give me the next one, or we can ask a question?
PbSO4 parentheses 2.
PbSO4 2. So we divide both of these by 2 because we still have the same ratios. Does that make sense? Doesn't come up too often. And honestly, you'll see on the practice test that I use lead there too, because lead's the only one I have memorized from when I've done this sort of stuff. But if I walk down the real test, I'll probably give you something else if I do one of these. I'll walk down the hall and I'll ask Dr. Hughes, who is an inorganic chemist, for a couple other examples, because he knows many more charges of multiple metals in the center of the periodic table than I do. I'm a biochemist. Questions on how to do naming? Does that seem good enough for going off and practicing more? Okay, so we hit all the kind of options that could happen there. Are you guys okay with trying to name covalent compounds from the compound? Or do you want to see a couple examples of that? You want to see some examples? Okay, let's go ahead and do a couple of those. I'm only going to give you 2 of something, so let's go ahead and say we named. I've got to go name. We're going to go names to compounds here. So let's say we had. Well, let's do carbon monoxide. I'll write down a few names and go ahead and do them, and then we'll catch up and write in the answers. Sorry, I'm trying to do real ones. Let's do silicon dioxide. Let's go with those. We'll do that. There. Okay, so carbon monoxide, what's the formula there? CO. Silicon dioxide, SiO2. Phosphorus pentachloride, what was it? PCl5, and dihydrogen monoxide, H2O, that's water. Does that make sense how those work? We're just going to take the number out front. We're going to name how many of the things we have. The only real trick here is we don't put mono when we only have one out front. Okay, other questions? 16 minutes left, yeah.
So if we have to go in reverse order from like H2O, can we just say water?
If I gave you water, you could just say water. If you know a common name for it, great. I'm not going to do water. I'll look something up. Okay. Yes.
Can you go over, like, briefly what we did last class with the tetra, like the structures?
Yeah, doing the structures and that. Okay. So you're going to need to know the structures based on how many things you have around it. So you need to know a set of names, really. Okay. On your homework, it asked about asked about electronic geometry. I'm only going to be concerned with molecular geometry. Okay, so we'd ask you about electronic and molecular. Electronic actually tells you the base shape, right? But the names are all different outside of that. So, so what we're going to do is, so how do you find the shape of a molecule? Is really the question. Okay, and then what you're going to do is draw the best Lewis dot structure. All right, and what I mean by best is you find the one that has the lowest formal charge, right? Best is going to be, actually I'm going to stop saying best, but we're going to say most stable because that's what best is. Lewis dot structure. And that's going to have the lowest formal charge. Okay, and you're going to break ties by putting the more negative charges on the more electronegative atoms. We're putting the negative charges okay, remember that electronegativity is a combination, kind of a combination of our ionization energy and our electron affinity, and electronegativity increases as we go this way and as we go up. Okay, there are actually numbers assigned to it. I'm going to be careful that I don't give you things where this trend is broken, if that makes sense. Okay, so a great molecule to give people involved nitrogen and sulfur for these loose dot structures, but that breaks our trend. Okay. Nitrogen is actually more electronegative. Actually, maybe sulfur is now that I think about it. But regardless, I'm not going to give you. We're not going to do the table. I will not break that trend. All right, so that you're going to draw that, and then you're going to determine the shape based on how many electrons, well, how many lone pairs of electrons, and how many atoms are around the center atom. And what's going on there is that we can think about them as electron groups, right? A lone pair is a group of 2 electrons. A single covalent bond is a pair of 2 electrons. But if you have a double or triple bond, they count as one group together. And so when you're studying for a while, that might be, I'm going to look it up on the table. And then after I look it up on the table, the next thing is, you should have that memorized. I'm not going to give you the table on the exam. I'm not going to give you the names, all right? If you feel like, hey, that looks like a triangle and I don't remember trigonal planar, take your best guess at a name and you can get partial credit for that, okay? All right, so let's go ahead and do one of these. I saw PF6. 6 minus on that. We had that website we were going to. I haven't tried it, so let's try it and see what it is. Okay, so PF6, what shape is this going to be? Anybody know already? It's got to be octahedral because you can only put 6 things around an atom. Okay. But it's going to be octahedral, but let's go ahead and figure it out anyway. So we're going to draw our Lewis dot structure. 1, 2, 3, 4, 5, 6. The first part of that is I've got to figure out how many electrons I have to play with. And so phosphorus has 5 valence electrons. I'm looking at the periodic table for that. 7, 7, 7, 7, 7, 7 for all the fluorines. 6 times 7 is 42, plus another 5 is 47. Ooh, odd number of electrons. I've got a problem. How do I solve that problem? I have 1 electron, right? So I should have another one. So it should be 48. So 48 electrons to make this. That's a lot of electrons. The next thing is I'm going to put one of these atoms in the center. Which one should it be? Phosphorus, because it's farther over to the left. So here we actually have a little breaking of our trend. No, we don't actually. Electronegative. It's less electronegative because it's farther over to the left and it's down from fluorine. Okay, it's also the first one listed, which if you're not sure is often a good clue too. So I'm going to go and put all my fluorines around it. I'm drawing a Lewis dot structure. I do not need to draw a shape when I do that, right? So the next thing is I'm going to connect all my fluorines with single bonds. The next thing is I'm going to go around all the atoms on the outside, make sure they have full octets, meaning they have 8 electrons around them. I'm working this rather than have you guys work it, which would be better practice for you, but I'd like to get a couple more of these done. This is important. Lewis dot structures is really important, so I want you to be able to ask questions if you're unsure of something here. And this one is going to be pretty easy because we're not going to have to do any double bonds or anything like that. All right, so let's see how many electrons we used. If we use 48, we're done. So each fluorine, I'm going to do it like this. Each fluorine has 2, 4, 6, 8 around it. There are 6 fluorines. 6 times 8 is 48. I'm done. You guys agree? All right. So all my fluorines are happy. They have 8 electrons. My phosphorus has 12 electrons. Is that a problem? No. Why is it not a problem? Because it violates our octet rule. We get to make octet rule exceptions. We get to expand our octet if we are in the third row or below. Okay, so from here or below, we get to expand our octet. We've seen that in examples with phosphorus and with sulfur. And gosh, we have those weird things where bromines and chlorines were in the middle, right? We've seen xenon in the middle. So when we're here or below, we can actually expand that octet if we need to make, when we need to, when we expand the octet, is so that we have no formal charges. All right? Yes.
The top right, it says 1E negative.
Yeah.
Which is that?
So what's the 1E negative? Good question. So this has a negative charge on it. And so that means it has an extra electron. And so I put an extra electron in. If it was a positive, okay, what you would do is you would take an electron away, do a minus electron. Good question. Thank you. All right, so let's go ahead and do another one of these, maybe one a little more complicated. Let's do nitrate.
So the name for that one's just octahedral.
Oh yes, what's the shape? Octahedral. Thank you. So the shape here is going to be octahedral, and that's because it has octahedrals when you have 6 atoms around a center atom. Okay. And the actual shape, and so you can do these by thinking about it. The actual shape is like a D&D 8-sided dice. Am I the only one who gets that reference? Okay, great. Thank you. I feel better. So this is like an 8-sided die for D&D. I took 2 art classes in college. Okay, they were fun. Anyway, so let's do nitrate. All right. When I look at nitrate, right off the bat, I can say, well, this is either going to be, could this be linear? Just in terms of double checking myself. Could this be linear? No, because I'm going to have 3 atoms around the center atom, right? So it could be trigonal-planar, okay? It could also be a trigonal pyramidal. Depends on whether I end up with a lone pair of electrons on that oxygen. But let's go ahead and just do our Lewis-Dot structure process here. So we have a nitrogen, I have 3 oxygens, and then I have an extra electron. Put 1. I'm just going to put electrons. But this is based on our charges. So nitrogen, how many valence electrons? 5. Oxygen, 6. We're just counting over from the left here. 6, 6, 6, 1. All right, so I've got 5 plus 1 is 6, so I'm going to have 4 times 6, or 24. Okay, 24 electrons is how many electrons I have to play with. Which atom goes in the center? Nitrogen. It's listed first, which is often a good clue. Might not always be correct, but and then it's also farthest to the left. It's the least electronegative. So now I'm going to go ahead and attach all these atoms to that internal nitrogen, and then I'm going to go ahead and fill up all their octets, and I'm going to leave that nitrogen alone for now. This is following the process we've got in our book. Let's look at how many electrons I used. So I used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26. Is that right? Did I do that wrong? Is it 24? Hold on. 8 times 3 is 24, right?
Yeah.
So I miscounted. Let me try again. 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 18, 20, 22, 24. I'm having issues up here. Okay, 24. It is 24. Sorry about that. So I now need, but is my nitrogen happy? It's not. I need to get 2 more electrons onto it. So how can I do that? I can make a double bond. I can take 2 of these electrons off of one of these oxygens and double bond it. All right, so now I'm going to end up with something that looks like this. I'm gonna go ahead and put my electrons in.
Does it matter which oxygen we make the double bond to?
Great question. So the question is, does it matter which oxygen I make the double bond to? It does not. And let's circle back to that. Okay, so any of them are okay, they're all equivalent. And so what we have here is, now let's count, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we've got 24 there, and does our nitrogen have 8 around it? It does, that's a good structure, all right? So the great question was, does it matter? And it doesn't. This is an example of our resonance structures, right? So I could draw like this. I can move those electrons around, is what I'm doing really. I'm not moving any atoms around. Or I could draw this. These are all resonance structures of each other. Okay, and do these actually exist? Is this flipping between all of these in solution? Is it sometimes this and sometimes this and sometimes this? No, it's not. That's not what resonance structures are. What is it?
Average.
It's an average of all of these. So if we were to do a measurement of how long these bonds were, and we can do that, we can shoot light at it and figure out how long these bonds are. We find that all of these bonds are, so I've got a double bond and 2 triple bonds, all of these are about a bond and a third in length, if that makes sense, okay? Let's go ahead, I have a whole minute here. Let me do formal charges, okay? So formal charges, remember formal charges are how we're gonna tell what's stable. Our formal charge equation is, it's the number of valence electrons minus the number of bonds minus the number of unshared electrons. Okay? Yes? What was the what?
The shape on the last.
Oh, what's the shape of this? Great, good question. So I've got 3 things. What's the shape? I have 3 things around the center atom. 3 atoms. No lone pairs. What shape is that?
Tree.
That's trigonal planar. So they're to get away from each other as far as possible, they'll make a triangle, a flat triangle. So trigonal planar. Okay, and I'm out of time, so I'm going to just tell you that if I run that equation for these atoms, I'm going to end up, each of these is going to be the same, right? I'm going to end up with this being -1, this is going to be -1, this is going to be +1, and this is going to be 0. So you see, I end up with this interesting case where I'm getting my best structure is a -1, but it's 2 negatives and 1 positive. Okay? Wish we had more time for a review. If you have time this afternoon, come tell me and we can make an appointment. Otherwise, please come to the study session and send me emails if you need help as well. Yes. Whatever you want.